Good morning or afternoon, class. Welcome to week 4 of the semester. This week we'll be talking about the grinding and polishing techniques and some of the consumables that go along with the metallographic preparation process. So to get things started, we're going to look at the overview. When we're going through the metallographic preparation process, there's essentially two completely different steps. The first one is grinding. So we'll talk about the process, the media that you grind with, and some of the equipment. And then step 2 is the polishing aspect, which also we will talk about the processes, the media used, the equipment, and we'll also discuss the differences, advantages, disadvantages to manual polishing or hand polishing versus the automated systems that are predominantly used in higher volume output laboratories. So to get started, the grinding purpose, or the grinding process, the purpose of it, what you're trying to do with the sample is remove any of the oxide layers, damaged layers, or uneven surfaces that were formed during the last operation. So if you just barely mounted your sample, your job on the first step is to grind through whatever sectioning technique that you utilize. So obviously, if you used a bandsaw, the damaged layers are deeper, and you'll have to grind through your sample more to get to undisturbed metal. Okay, so this is typically accomplished by abrading the specimen surface using progressively finer abrasive grits. So if you're familiar with like how you would sand down a car to prepare it for body work, sand wood samples, you start off with a coarse grit and then work your way to the finer grits for that very nice finish. So there are two different types of grinding categories. The first one is the coarse abrasive, and those are grit sizes that range anywhere between 60 to 150 grit. And then you have the fine abrasives, which are in the range of 180 to 600 grit. I'll get to their micron sizes here shortly when I show you guys the chart. So during the grinding process, the best way to start is going to once again depend on how you section your sample. So you're going to start with the finest grit size possible that can establish a single plane across the entirety of the mount. So if you started off with a hacksaw or bandsaw, then chances are you'll need to start with 120 or 180 grit in order to get your entire sample on one plane, and you've removed the effects of the disturbed metal caused by that particular sectioning process, which for that example was the bandsaw or hacksaw. This is the most important step when it comes to the preparation process. So once again, how you section your sample is by far the most important step, okay, because that determines how you're going to proceed with the grinding process. So as we look through, all the grinding steps should be performed wet, as long as the water doesn't have any adverse effects on the constituents in the microstructure. Some metals don't like water, so you might have to grind with an ethanol or glycol-based alcohol or glycol-based lubricants instead of water. But once again, those would be specified depending on your sample preparation process. So if you were, for instance, wanting to polish magnesium, magnesium doesn't like water, so you would use a glycol or alcohol process instead. So why would you wet grind instead of dry grind a sample. Well, if you dry grind a sample, you essentially heat up the sample. There's nothing to lubricate or cool. And so that, of course, is something that we're trying to avoid, especially, especially during long durations. You're using these papers anywhere between 30 seconds to a minute long. So if you left a sample on the on one of these abrasive pads for that amount of time, the sample ends up becoming way too hot for you to touch, and you can actually burn your fingers. So you want to minimize that heat, so you don't have to drown your sample in water during this process, because you do need some contact with the abrasive on the sample. Too much water, your sample will hydroplane, just the way you would if you were driving 70 on the freeway and hit a puddle of water. You hydroplane, and now that you don't have contact with the surface, you actually round out your edges. So you're defeating the purpose of having any edge retention on your sample. And the other reason why you wet grind is to also prevent the abrasives on the surface from being overloaded. So as you are removing metal, that metal stays on the pad, and if your metal is now overloading that pad, you're no longer going to be abrading the surface, and instead you can create an issue with material being smeared back onto your sample. So the wet grinding process kind of helps remove the particulates that are being abraded off, off the pad, revealing still fresh abrasive for the cutting surface. So each one of the grinding steps will create its own damage layer. So that's why after sectioning the sample, if you were to hacksaw, you have to start off with a 120 or 180 grit. If you used an abrasive cutoff wheel, you could probably start off with a 240 grit. And if you sectioned your sample with the precision diamond blade, which would put the minimal amount of damage, you could probably start that step off at 600 grit for your start point in the grinding process. So as your grit size decreases, you have to think that the depth also decreases, right? You're not going to have that same depth of damage to your sample a 120 would create versus a 240, a 320. So in order for you to remove the damage caused by a 180 grit sample abrasive paper on your sample, you would then need to move to 240 and ensure that all that damage is removed. So you might have to spend a little bit more time on your sample than the previous step. So softer metals tend to, damage easily versus hard metals. That's why hard metals are so easy to prepare versus soft metals. What's an example of a hard metal? Any steel is considered to be a hard metal. So steel samples are very easy to prepare. Soft metals like aluminum or copper tend to be the ones that give everybody a headache and really test your patience, because the amount of damage that you can create on your sample is an issue. But also when it comes to scratches, since they're soft, any particle that's slightly harder than that material will scratch your sample, giving you not so pleasant results. So commonly used grinding abrasives, the one that's widely used and more readily available is the silicon carbide discs. You essentially have silicon carbide that's embedded onto these waterproof papers that can either be fastened to the metallographic wheel, or they have an adhesive back that you can applied to the wheel, kind of like a sticker. Alumina as well, but since silicon carbide is more readily available and cheaper, that's the one that's used more often. You do have emery ceramics, not ceramics, but ceramics compounds. It's a combination of alumina and magnetite, which is Fe3O4. That's rarely used nowadays. I just thought I would mention it because that's how a lot of this metallographic preparation process started. But it has very low cutting efficiency, and in today's day and age, you kind of want to get stuff done on a more rapid basis. And then, of course, you have your diamond compounds, which are typically used on napless cloths. So some of the standards, silicon carbide papers have two different standards. You have the standard for the United States, which is the ANSI-CAMI standard, and then you have the FIPA standard for the silicon carbide papers that are manufactured in Europe. The differences between the two of them is that the advantage of the papers manufactured here in the States is that it uses a wider particle size distribution. So the mean size will give you faster cutting rates at lower pressures. And that because you have faster cutting rates at lower pressures, you generally generate less heat and damage into that sample. But the disadvantage is because you're using a wider range of particle size, then the larger particles within that mix can give you deeper scratch depths, and that's one thing we want to prevent. Now, of course, when you move to the next step, you're supposed to grind through the sample and eliminate any of that damage caused from the previous step. So is it really a disadvantage? Probably not. I think it would be more problematic as you move from the grinding discs, like the silicon carbide discs, into the diamond or final prep process. So to look at the micron sizes between the FIPA and ANSI, or Europe versus US standards, one of the tips that I'll go ahead and say right now is you need to stick with one or the other. You cannot do a mix and match. And it might not be problematic in the beginning, because if you look at these areas here, I'm going to use my blue marker. If you look at this area right through here, they're pretty much on the same grit size as what you see here. So your P60 grit or 60 grit paper, 269 micron versus 268 micron. Okay, not a problem. But we're not really starting with these ones up here at the top. We're really starting with 120 to 180. Okay, so when you're looking at the 180, well, they're about the same grit size for both. Okay, then you look at the 240. This is 58 to 66, 52 to 51. Typically, when you're going through this process, after 180, you'll hit 240, from 240 to 320. So here's a 320 here at 46 micron, but the 320 on this side is 34 micron. Okay, so maybe it'll be better if I were to highlight. So here's 120. Here's 120. Okay. Then we're looking at 240 as the next step. Here's 240 here on this step. We'll look at 320. And here's 320. Do purple. I typically skip the 400 step and go to 600 when I prepare my samples, and I'll explain why in a little bit. But here's 600 versus 600. And after the 600 grit step, I typically jump into my diamond polishing. But when you look at the 4 steps that I've highlighted, look at the differences in the micron size associated with each of the grit papers. Like I mentioned before, 120 grit, not that big of an issue, but 240 to 240, you know, not too bad. 320 to 20, you're looking at about a 12 micron difference. And then you're, like I had mentioned before, look at the micron difference at the 600 grit 600. You have 25 to 14. So moving to 9 micron diamond paste after this, it would be easier for me to prepare samples that are from this category, because the last micron size is 14.5 versus jumping from 9 micron, jumping to 9 micron from 25 micron. I'll have to grind much longer, and that wastes a lot of time, a lot of prep, and you also risk rounding out your samples. So if you were using the Europe-based silicon carbide, you might have to jump to the next step, something that's in between 25 and 9. So in that sense, you would probably introduce a new step at either P1000 to P1500 in order for you to jump to a 9 micron or 6 micron jump. Okay, in order for you to be on the same page as a 600. So when you're looking at that, if you were to start mixing and matching, there's a chance that if you jump from a 320 over here and then go to use a 600 grit, or let me see, how can I do this? If I went and I used a 320 over here and I tried to use a 600 over here, the jump between 46 micron to 14 micron is so large that I'll end up doing more damage to my sample because I'll have to spend more time on 600. So your best bet is to stay with one category when it comes to using grit sizes in your preparation process. So some of the equipment, what's pictured here on the left, a manual or hand polishing table. The disc that you see, this is where your abrasive paper will go, and you have the water that comes out of this faucet here to help distribute the water onto the pad as it spins. This right here would be your RPM controller, so you're able to control the speed of the wheel. Speed is also an important factor when you're polishing your samples. Once again, I have illustrations on what speeds you should use during the polishing and grinding process. And the one on the right side is an automated or semi-automated polishing station, where it's already hooked up to all the different slurries for polishing, and you can set the parameters necessary for the crosshead, which is this guy here, and the table. So as this table spins, the crosshead also spins, and that gives you even distribution to plane your sample on all sides. So in the polishing process, this is the final step. And so after your, depending on where you end your grinding steps, this is where you jump in to provide that deformation-free surface, and it looks like a mirror. I kind of joke around all the time talking about, you know, we're not, as metallurgists, we're not conceited because we always want to take a look at ourselves in the mirror. But that's one way that you can check if you have a scratch-free surface, is every time you pull your sample off of the table, you're actually looking at yourself. So it always seems like we're conceited, but we're really not. It's a scientific thing. So once again, just like in the grinding process, you have two different categories in the polishing process. You have your coarse polish and then your fine polish. Your coarse polishing is anything that's between, actually it's anywhere between 15 to 3 micron. I typically use 9, 6, and 3 micron. And then for final polish, I typically stop at 1 micron. I don't have to proceed any further than that. It is necessary for these steps to provide the true microstructure for the interpretation, testing, and analysis, whether it's quantitative or qualitative. If you do not complete the polishing process, the amount of scratches and or deformation still on the surface hide that true microstructure. So also, since you are in this step, this step is not there to introduce unnecessary structures or other anomalies within that on your sample. And such structures I'm talking about is deforming or disturbing the metal, grain or inclusion pull out, staining, or create relief between the constituents or holes, you know, like porosity, shrinkage cavities, and that nature. And I have some images to show you based on those. So your coarse polishing begins in that 3 to 6 micron range, and you're performing this now on a napless cloth, typically nylon or silk. These cloths are dependent on how they're woven. They do not have fibers that come off of the pad. It's just a woven napless cloth. And the reason why we use these is to help with that edge retention. Edge retention is a must. It also helps with the sample flatness. So the coarse polishing, if you're using 9, 6, or 3 micron, all of that is performed on a napless cloth. Then when you get to the final step, your final polish can also be done on a napless cloth or a low nap cloth, something that has short fibers, using 1 micron diamond. Each step must have a compatible lubricant. Once again, you can still overheat your sample or deform the surface if you do not have adequate lubrication on that pad. Once again, you don't want to drown your sample either. So the purpose of this week's lab is to show the techniques and the amount of usage for each of these consumables that we'll be using. The intermediate polishing step should be performed thoroughly enough so that when you hit final polish using 1 micron, you spend the least amount of time. Once again, you can at that level still round out your edges if you waste too much time on the 1 micron polishing step. You can create a lot of relief between a hard constituent versus a soft constituent. For instance, in steel, if you have, if you're looking at perlite, your soft constituent in that case would be your ferrite. Your hard constituent is going to be the cementite. So if you have something along those lines, you can create relief. And if you were doing any type of interdendritic, interlamellar spacing calculations, that could provide you some issues. Each of the polishing steps, starting with, I typically start at around 6 micron, should be conducted with you rotating the specimen counter to the rotation of the wheel. And once again, majority of these samples can be prepared adequately and accurately to where you can interpret the data after 1 micron diamond. I don't find it necessary after 1 micron diamond to jump into the 0.3 alumina, 0.05 alumina, and I very, very rarely ever use colloidal silica for any of my polishing. So what are some of the disturbances that we can create in our metal that can lead to misinterpretation? So what you see here are 3 images. and I can zoom in a little bit on these guys so you guys can take a look at them. Okay, so what you see in these three images here is this right here is titanium, and what happened is during the process it formed some mechanical deformation. Well, if you didn't know any better, you would think that this is a completely different constituent, and because of its acicular nature, you would probably call it some type of an acicular structure with equiax grain structures. Okay, well, this is commercially pure titanium, so it's going to be very soft, and since it's soft, you have a tendency to create mechanical deformation. So that right there would already lead to a microstructural misinterpretation of what you're really seeing. For this next one here, just by the naked eye, this arrow here is pointing to some of these dark, features that are on this unpolished or as polished surface. And what you're looking at is either grain or carbide or inclusion pull out. So what used to be there was a carbide or a grain. Grains can pull out. They are crystalline. They can pull out of your material. One of the ways that you end up with grain pull out, carbide pull out, inclusion pull out is if you use too much pressure on a cloth that is napped. So if your cloth has fibers that come up off of the pad itself, these fibers tend to kind of snag these and pull them out. With too much pressure, that's bad news. You would say, oh, look at all this porosity this sample has. So there's another misinterpretation, because then the client would ask you, how did porosity enter our material if it's not a cast product? Okay, so that would be a way to misinterpret what you're looking at in the microstructure. The last one is a steel component, and what you have is a very common issue. These are comet tails. You can see that wherever you see a hard particle or carbide, you see this comet tail. That's exactly how it got its name. This shows the direction that it stayed on the pad for too long a time, and you do not have an even wear. So what happens is the particles will kind of interact with your particles, which you can see are in relief. They do look like they're indented into the material, and then you see this pull out. So that's where the particles from your final polishing process have kind of created a wear zone for how they leave this region. So the way that you can avoid this feature is that rotation counter your the wheel. And what the wheel will then do, instead of you sitting in one place and holding it there for 5 minutes while you talk to your friends, if you rotate it the opposite direction, because the wheel is spinning and your sample is spinning, you're attacking these particles in all directions, so it does not give the particles the opportunity to create these comet tail features. So when it comes to polishing cloths, what makes a good polishing cloth? How do you know what to select? Well, for one, you have to select a cloth that's going to hold the abrasive media that you are willing to use. Not all cloths are created equal. Some cloths are meant to hold, 9 micron, 6 micron, but they would perform horribly if you're using it for 3 micron, 1 micron, and of course anything smaller than that. You have to have a polishing cloth that has a long life. And of course, an absence of foreign material. You will not use a polishing cloth that you just polished, I'm going to say tool steel, and then try to go polish an aluminum sample, because The tool steel being a much harder material, you still have abrasive tool steel particles on that pad that will scratch your aluminum, and you will never have a perfectly polished aluminum sample. Vice versa, if you try to polish aluminum and then try to polish a steel component, since aluminum is softer than steel, there's a chance that you could smear the remaining aluminum particles onto your steel surface. And, just to kind of jump into etching, when you etch that sample, the same etchant that's used for steel does not etch aluminum. So when you etch steel with nitol, the aluminum will be left unetched, giving you, once again, a misinterpretation of what you're seeing for that microstructure. Since cloths are composed of different fabrics, weaves, or nap, that's why you have to choose what's best. What are your best available options for your sample prep? Napless or low nap cloths are recommended for with diamond abrasive compounds for your coarse polishing, and medium to high nap cloths are used for final polishing, but this is where you need to minimize that your use at this step, because your edge retention and relief become compromised. I typically still stay with low napped cloths when I finish my 1 micron diamond suspension. Polishing abrasives. Once again, you have diamond compounds, aluminum oxide compounds, and amorphous silicon dioxide, which is what you find in your colloidal suspension. Your synthetic diamond compounds, I never use monocrystalline. I use the polycrystalline synthetic diamonds because you end up with faster cutting rates than monocrystalline diamond compounds. And the reason for that is because it's a polycrystalline compound. As these polycrystalline diamonds abrade your sample, they themselves will break into smaller fragments, which freshen the cutting surface. So you're always freshening the cutting surface with a polycrystalline diamond compound. Then you have your alumina oxide, alpha alumina. It's got you can get one that has a low pH or a high pH. Once again, it's going to depend on your sample. But 0.3 micron and 0.05 micron slurries are typically used. I don't mess with alumina very often at all. And then the last one is your colloidal suspension. The silica particles, believe it or not, they're spherical, nearly spherical, and you have about a pH of 10. So this process is very slow in the aspect of mechanical and chemical polishing. So if you're using a colloidal suspension, chances are you have a greater chance of rounding out your edges. I never go to this length. I believe your aluminum oxides and colloidal suspensions are best used in the vibratory polisher more so than the mechanical or manual or automated polishing steps. So what about the polishing equipment? Look at that. It's the same as what you use for grinding. There's nothing special. The difference is the cleanliness of your station. So if you're going to be grinding and polishing using this the manual side, then you got to ensure that you clean the station between each step, especially when you get down to your finer micron sized abrasives. You cannot use this wheel 9 micron if you just did 600 grit and not clean it, because those particles do somehow always find a way onto your pad. And as a metallographer, you will get agitated if you do not have patience. It's better to take 30 seconds to clean in between the steps instead of spending a whole day trying to fix a sample. Remember, sample prep is important, especially if you're trying to hit a specific target. You can't grind through your entire sample and say, oops, I lost my sample now. Okay, so cleanliness is number one. So using these are once again some of the different types of polishing cloths that are used for the intermediate polishing process. So you can see that nylon pads here are good for your 6 and up micron. Diamond, they're oil resistant, medium hard woven, no nap, so it's napless. This has helped to retain flatness and hard phases, and it's great for ferrous materials, sintered carbides, or cast irons. So you see how each of these are going to be good for whatever you're looking at preparing. So looking at this list, here's another one, Veltex. Each company has different names. These are all Buehler brands. So if you ever wanted to look up, like if you're going to order from Lico, Buehler, Struers, Pace, who's another brand, Allied, they all have different names, but essentially they would have a description of what they're best used for. Okay, but just taking a look at some of these, you can see that, you know, some of them are good for only a good range. So I use nylon. This is what I use for my 9 to 6 micron, and then I jump into something like this for my, or something like this one at the bottom that might be there for my 3 and 1 micron step. Then those are intermediate. Here's your final or your fine polishing. Master Text, this is probably the one I would end with, just because it has low nap. This one here is long nap, soft porous synthetic cloth. It doesn't specify a nap on this one. But if I remember correctly, I think this is also a low napped cloth. But once again, it tells you the sizes and also your abrasives that are best used for each of them. So when it comes to manual polishing, I got a couple tips. The first tip, if you're going to hold it by hand, obviously this is going to be the manual polishing. I recommend 2 hands. Believe it or not, it's going to be the control of the sample more than it is the pressure applied to the sample that give you the best results. If you cannot place the mount on the disc without the sample wanting to fly out of your hand, you'll never want to polish again. So one of the best things to do is hold the sample with 2 hands. And once again, I'll demonstrate that in the labs. And of course, you guys will get a taste of that when we get into the labs. But you're going to place it not in the very center of the pad. Since it's spinning, if you place it a little awkwardly, it'll take your sample out and you're not going to have a... So what you do is just go just to the right, just below. Once again, I'll discuss sample placement on the pads when we get into the lab. We'll have a video showing all that stuff. But you want to place it just to offset from the center. That happens to be the part of the wheel that does not have the angular velocity that you would on the outer edge. So the chance of the sample flying out of your hand is far less by being placed closer to the center. Once control has been established, then you can move the sample after staying in your spot for 5-10 seconds. Now you can move to the outer edge and move back to the center. By you doing that, you are now being able to ensure even distribution of the abrasive particles on the pad, or an even distribution of particles on your sample, and uniform wear of the pad, because you're utilizing the full 8-inch pad. If you had a 12-inch pad, same thing. You're going to utilize the whole pad. You do need to have a firm hand pressure, but control, once again, is going to be key. Hand pressure, I mean, I don't have calibrated hands, but I try. It's hard to explain. You're going to have to do that by experience when you place samples. Softer samples will require less pressure than harder samples. Tip number 4, washing and drying the sample under using running water. Warm water is preferred. Just like when you wash dishes, it just dries faster and cleaner, more spotless. And then you rinse it with ethanol, and you can dry it using either the compressed air or a stream of warm air if there happens to be like a hair dryer in the laboratory. Cleanliness of the specimen, your hands, and the equipment is a must. That is definitely a must when it comes to this, especially if you do not want to polish your sample for long periods of time. And then the last one is to change the orientation. So previously I had mentioned that you have to get rid of the previous damage created by the polishing or grinding steps prior. And this is one of the ways that you could kind of determine that. Other books will say, 90 or 45 degree orientation changes. I do 180 degrees just because it's easier to, because the disc is circular. When you have a 180 degree change, you're creating a smile on your face. So changing it 180 degrees, you're able to then turn that, turn the smile the other direction. I was going to say turn your frown upside down. But anyway, it just helps you visually confirm that all the patches are gone from the previous step. The automated polishing system, well, you're essentially doing everything that you wanted to do manually, but instead of you holding the sample, it is fixated in its own mechanical device. And this particular method, you're able to produce higher volumes of samples. And on top of that, the big advantage is you're able to produce those samples with higher quality than your manual polishing methods. It helps you reduce your consumable costs, and it does produce the best edge retention and surface flatness, because when you're manually polishing samples, are you exactly putting that sample flat every single time when you lift your sample off to put it back on? So in case in point with this here, since these are fixed and you have a crosshead that drives the sample with force, they're always in the same position at all times. So that's what produces your best edge retention. So some of the, this is a generic, I'm not going to say generic, this is a general preparation. If you were using a automated system, so think about it, automated or not, you would still go through each of these steps that you see here for the abrasive, okay? So going through, let's say we cut with the bandsaw. So we can go ahead and eliminate this guy. Okay, so we're going to start at 240. Well, skip that. Let's say we cut with something better than a bandsaw. We cut with the abrasive cooled wheel. Lubricant cooled abrasive cutoff wheel. So we're going to start with the 240. Okay, and then we do 240, we go to 320, 400, 600. And you see from 600, you're jumping to 6 micron and then 1 micron. And I typically do not go through these two last steps. Okay. So we can scratch those two out. So you have 1, 2, 3, 4, 5, 6 steps to go through. And the next thing to look at is the force. So you're looking at 6 pounds of force that you're going to be putting on the sample. If you were using an automated system and you loaded that system with 6 samples, then you would not, when it comes to selecting the load applied, you would have to take 6 and multiply it by 6 because you have 6 samples and each sample needs 6 pounds force. So with that being said, the force that you would set then would be 36 pounds force. And that would give you the 6 pounds necessary for each of those samples. If you just set it at 6, because it says so here, then that's only going to give you 1 pound force on all 6 of those samples, which means since you're not putting a lot of force, you're going to be wasting more material because you're not grinding through at that given a certain load. The next thing to look at is your base speed. So you're operating between 240 to 300 RPM. I have kicked people out of the lab for revving it up to 1,000 RPM and trying to polish harder samples. So I do not want to see anybody in the lab misusing the wheels in such a way. The purpose of not using high RPM is, what do you think happens to the sample if you're trying to grind and polish at 800 to 1,000 RPM? For one, the chance that that sample flies out of your hand and hits somebody is very high. You do not know how the wheel is going to behave if you're also applying a load to that wheel. And second, third, fourth, fifth, it doesn't matter. You burn your sample. You overheat it. You cause mechanical deformation. And you're not really preparing your sample appropriately. So 200, 240 to 300 is typical range when you're in the silicon carbide grinding stages. Okay, and you can see that's carried out all the way till you get to about here. You maintain the same. Now you see that when you reach the polishing portion, all of a sudden the force stays the same, but your RPM now decreases. And that goes into not wanting to create anomalies on your final polishing surface. So you decrease the base speed and you increase the time at which you're polishing your sample. This prevents your carbide pullout, your grain pullout, inclusion pullout, disturbed metal on soft materials. This prevents edge retention issues because your mounting material is softer than your metal that you're polishing. So this is the reason why you decrease the speed, is to help prevent those unwanted anomalies that you would get on your final sample. So for your assignment on week 4, once again, if you haven't done it already, sign up and complete your EH&S safety. As we're moving through, we are getting closer and closer to getting you guys into a laboratory setting. Complete your weekly summary. These are going to be due Sunday by midnight. Week 4 quiz, I'll be posting that up sooner than the last one that I did, so I apologize for that. And then we will meet on Friday for the lab. The mounting and grinding and polishing topics will be covered. So I will start by mounting a sample using a hot mount and go through the metallographic preparation process up to the final polish. and which will then lead us into week 5, which I believe we will be talking about etching and microscopy. So that concludes the grinding and polishing process. If you have any questions, please feel free to shoot me an email. I mean, that's what the labs are going to be for. Address any issues. If you have scenarios that you want to talk about in the lab as well, please feel free. The floor is yours as well, and we can talk about that stuff in the lab. So I'll see everybody on Friday, and enjoy the rest of your week. Thank you very much.